Hi everyone. I am happy to present to you this talk, Redis and Line, 25 billion messages per day. My name is Jongyeol Choi. I am from South Korea, and I work at Line Plus as a software engineer. I am a member of the Redis team at Line, and our team has members both in Korea and Japan. As you can see from the map here, the headquarters of Line is in Japan, and we have offices around the world. I have made some contributions to Netty, Letters, and other open source projects. Today's topics. First, I'll start off with introducing Line's messaging system and storage system, and move on to our in-house Redis cluster and scalable monitoring system. I'll share our experience with the asynchronous Redis client and also the official Redis cluster. By official, I mean the one from Redis open source. Well then, let's get started. Line is a popular messaging service with more than 168 million active users across Japan, Taiwan, Thailand, and Indonesia. Line delivers 25 billion messages every day. At the midnight of the last day of the year, one of the peak times of the year, 420,000 messages get delivered in a second. I guess people have this thing going for being the first one to say Happy New Year to their friends or family. Along with the messaging service, Line has many family services. Today, we are going to look at Line's messaging system. Line's messaging system has many server components, messaging server and asynchronous task processor, which are core components, and many others, including API gateway, authentication, bot, shop, and timeline. The messaging server, which has the most messaging features, is developed in Java and with Spring, Thrift, Tomcat, and Armeria. Armeria is a RPC framework and is a Line's open source project. Another core component is the asynchronous task processor systems. To handle user requests through API calls, we sometimes need to run tasks in the background rather than in the foreground. To do this, we have been using a local Redis queue on the same machine used by the messaging server for data locality. Recently, we've added Kafka for processing async tasks that take time. For messaging server storage, we use Redis, HBase, and Kafka. First, Redis. We use Redis for two types of data, cache data and the data stored in the primary storage. Cache data implies short-lived data, or the data in the origin storage. If the origin storage can accept failover traffic, a Redis cluster may consist only of masters. Primary storage contains data that is almost persistent or has a long lifespan. For our primary storage, we set up our Redis cluster with one master and one slave per shard. Second, HBase. HBase is used for persistent data or backup storage. When we need to handle cold data in terms of business logic, we use HBase only. Also, when Redis fails, we use HBase for backup. I'll come back to HBase later to show you how we used it with Redis. Lastly, Kafka. We use Kafka for processing background tasks, as I mentioned earlier. We also use it for delivering important data to other server systems. If you want to get detailed information on our usages of HBase or Kafka, you can find our presentations on one we did. Please Google HBase at Line Developer Day or Kafka and Line at Kafka Summit. Since we are here for Redis, so let's focus on the parts related to Redis. We are using Redis versions from 2.6 to 3.2. Once we set up a cluster with a particular version, we don't upgrade Redis used in the cluster without a specific reason. Because upgrading Redis on a live Redis server is impossible. If we were to upgrade Redis, we'd have to migrate data to a new cluster with a new Redis version. We have more than 60 Redis clusters, and most of them are in-house Redis clusters. and the rest are the official Redis clusters. We run more than 1,000 physical machines that runs 8 to 12 Redis processes each. A physical machine uses 10 to 20 CPU cores and has 192 to 256 gigabytes of memory. In total, we are running more than 10,000 Redis nodes, or rather 10,000 Redis processes on our clusters. The maximum number of Redis requests per second per node is capped 100,000. There are more than 370 billion Redis keys and more than 120 terabytes of data altogether in our Redis clusters. Some of the clusters in our messaging system contains 1,000 to 3,000 nodes in them, including slave nodes. Here, you can see a simplified version of the architecture of Line's in-house Redis cluster. A cluster consists of shards, and a shard consists of a master node and a slave node. We distribute data on the client side. We shard with keys without proxy. The Line Redis client library uses Redis and Redis and contains Redis commands. We have adopted two types of strategy for sharding: fixed size ring and consistent hashing. We keep the information of the shard structure in the zookeeper cluster. When the structure is altered, the cluster manager server updates the structure in the zookeeper, and every Line Redis client updates the changes in the associated application servers. When a Redis request comes afterward, the target shard for the given key would be changed. The Redis Cluster Monitor is a monitoring system for the in-house cluster for generating stats for all our Redis cluster servers. The monitoring system comes with other useful features as well. Many companies use a proxy system like Twin proxy, HA proxy, Dynamite, or Envoy proxy with Redis, but we don't. Let me tell you why we don't. Going over the pros and cons of being proxyless. The first merit of not using a proxy is short latency. In general, the average response time on client side ranges from 1 to 200 microseconds. Latency is a critical factor in a messaging system. Imagine having a chat room with hundreds of users. Each one of them has their own inbox storage for message IDs. When a user sends a message in the chat room, our application server would be writing the message ID hundreds of times. It's a massive operation and can take time. Everyone in the chat room would expect their message to be delivered at the speed of light. I don't think anyone here would expect or even want to have your message take a few seconds to be delivered, right? Time is critical, so latency is an important factor in a messaging system. The second merit of not using a proxy is cost efficiency. We have thousands of application servers and tens of thousands of Redis nodes. If we use proxy servers, we would need at least hundreds of or thousands of proxy machines. A proxy machine may cover many Redis nodes, and if the proxy machine crashes, many Redis requests would be affected. Bigger the coverage, bigger the after effects at failure. However, there are also drawbacks in not using a proxy. To use an in-house cluster without proxy, you would need to make an in-house Redis client, which would be written in a specific language. Since we are proxyless, we have an in-house Redis client, which is developed in Java, and so is our messaging server. The Redis client has all the code for sharding. If we modify the code for sharding, we'd have to deploy the new code to all application servers. Maintenance can be costly and problematic. Our cluster manager server checks all our Redis server nodes every 2 seconds. If a master of a shard doesn't respond for 20 seconds, then the cluster manager server sets the slave of the shard as the new master and updates the cluster structure in the zookeeper. This series of actions is called automatic failover, or some call it auto-promotion. Application servers will get the updated cluster information from Zookeeper eventually. Note how I said eventually. Getting updates cannot be atomic. Our system is a distributed system. At any given point, there is a possibility for applications to have different cluster structure information. If all data is immutable, non-atomicity is not a problem. But if data is mutable, and if different applications write data for the same key in different Redis servers in different timings, then data integrity can be compromised. To keep data integrity, what we did is add states to a shard: normal state, recovery mode state, and failure state. Think of recovery mode as a cooling down period. The cluster manager server updates the state in the cluster in 2 steps. Firstly, sets the shard in recovery mode state, and then a few seconds later, changes the state to the normal state. When a target shard is in the recovery mode, application servers do not send any Redis command to the target shard. Instead, they wait until the target shard enters the normal state. It guarantees all application servers have the same information for the target shard at the same time. This way can cause a busy thread problem on the Tomcat side. But the problem is bound to a single shard. I mean, it's a small part of a whole Redis request. Sharding rules and resizing. We have 2 types of sharding strategy used in our in-house Redis cluster. First is consistent hashing. Consistent hashing is widely used by cache systems, allows dynamic resizing, and works well with immutable cache data. But using consistent hashing with mutable data can be a threat to data integrity, especially with distributed standalone Redis servers. We did implement consistent hashing, but we have now adapted this in production. But we do Redis clusters with a fixed size ring strategy. Implementing and balancing data distribution with a fixed size hash ring is easier. However, dynamic resizing is not available with this strategy. So instead of dynamic resizing, we migrate data to new and bigger clusters when we need to expand our Redis clusters. When we expand our clusters, we usually double the size, and during the migration, all application servers access both old and new clusters. We migration tasks in the background. If there is a lot of data, migration can take several days or even a few weeks. During migration, because both new and old clusters are accessed, the average API response time of applications becomes longer than usual. Don't know if you remember, but as I mentioned earlier, we use Redis not only for cache, but for primary storage too. When we use Redis for primary storage, we always have slave nodes in clusters. Now, what would happen when a master node and a slave node crash at the same time? Or what if all the machines get restarted? We can lose all the data in the memory. For data persistency, you may consider using Redis RDB or AOF. But if you opt for this, the average Redis response time will be affected. You will experience longer latency or more latency peaks. But we do have needs for persistency, which led us to bring HBase into our system. Our application servers write valuable data to both Redis and HBase. To use HBase and Redis together, we've adapted dual write and HA, higher availability for reading. Dual write works like this. the application writes data to Redis first. When the application server succeeds storing data in Redis, it then writes data to HBase in the background. Data is stored in HBase by another thread. Or if this fails, it gets stored in the local Redis queue or Kafka first, and then the asynchronous task processor takes it and stores it in HBase. The reason why we do the writing in the background is to reduce latency. Storing data in HBase takes longer compared to Redis. As for reading, an application server reads data from Redis first. If a response does not come in a few hundred milliseconds, the application server sends a read request to HBase too. Then either one, Redis or HBase, will return a response. Then the application server will use it. In most cases, applications get responses from Redis first, usually in a millisecond. Sending read requests to HBase doesn't happen often, but it sure helps when Redis becomes slow temporary or Redis machines down situations. Hotkey. When we use multiple nodes using sharding by keys, there can be hotkeys. If all application servers access the same key at the same time, the maximum number of operations per second per node can be high easily. Also, the CPU usage can be 100% too, and we may see a lot of slow queries in our slow log. This can result in slowing down other Redis requests made to the shard, and also increase the latency in responding to API calls made to the application servers. So, how can you avoid this? If the commands for the hotkey are write-intensive, there is a little room for improvement. Redesigning key is the only solution. But if commands are read-intensive and the target data is cache data and immutable data, then using multiple slaves or multi-cluster will solve the hotkey problem. We use multi-cluster instead of reading data from slaves. We call these clusters replicated clusters. To increase read scalability, applications write data to and read data from a random cluster in the replicated clusters, only for the cached and immutable data. It can increase read throughput easily, and it depends on how many clusters we use. When application servers access a random cluster, which happens to be unstable or has crashed, the application servers access the origin storage, and next Redis request will be directed to a different cluster. When we add more cluster, we warm up the new cluster to increase cache-hit ratio before we add it. It can take several days if there are many keys. Next is timeout. Timeout is the most important factor in a distributed system. Sometimes a Redis shard or machine runs slow or crash due to many reasons. One of the possible causes can be running Redis commands like hgetAll or smembers for reading all members from a hash or a set at once, or del command for deleting a huge collection at once. It causes a long blocking situation in Redis because Redis is single-threaded. Another possible cause for latency is a hardware failure or temporary network problem. More machines you run, higher the possibility of having hardware failures. It is possible to have multiple problems with machines or network in a single day. In the cases I've listed, applications may wait for Redis responses longer than usual. And if thousands of applications wait for millions of Redis responses, you will end up with a busy thread or a full queue, affecting other systems as well. If you set your timeout short, you may be able to avoid these cases. However, timeout may not be enough. So, to supplement the timeout, we've added a circuit breaker a few years ago. We call it the anticipator, and we use it for clusters that contain important data. The goal of anticipator is to predict failure and don't bother Redis servers when they are busy. When latency increases, the anticipator module determines failure and records the target shard as in failure for a few hundred milliseconds. An application will look up the record, and if the target shard is in failure, then the application marks the result of its request as in failure without sending the request at all. After half a second, the application tries to send the request to the shard, and if it succeeds, the state of the shard becomes the normal state. The anticipator is very helpful in avoiding spreading outage to other server modules. It's worth having one. Next is Scalable monitoring system. The in-house standard monitoring system shows hundreds of metrics with minute precision. But with Redis, minute precision is not enough, because command busting, by which I mean many requests being sent to the same key or same shard, can happen in such a short period of time. So we built another monitoring system just for Redis, called Redis Cluster Monitor. It shows Redis metrics with second precision. Redis Cluster Monitor checks the status of Redis nodes every second using the info command and puts aggregated metrics into Elasticsearch, and we see the metrics on Grafana and Kibana. The sum of all info command responses can exceed available network bandwidth in a short time. So we use multiple Redis cluster monitor servers, and we distribute request timing of the info command for network bandwidth. And we use Akka clustering to handle failover of each Redis cluster monitor server. One of the essential features of Redis cluster monitor is automatically detecting command busting or connection busting. When Redis cluster monitor recognizes a busting pattern, it captures the Redis commands of concern using the monitor command and stores them into Elasticsearch. There are some metrics for recognizing patterns. For example, if operations per second locates often, or count of connections does, the associated Redis commands will be captured. You can see the information on Kibana, and we identify the cause and fix whatever is required to prevent command or connection busting. So far, I've talked about our in-house Redis cluster. Now, I'd like to talk about the official Redis cluster. As I said earlier, dynamic resizing is very difficult with our in-house Redis cluster. However, dynamic resizing is something we really want and need, and Redis cluster supports it. We take Redis cluster as the community standard and expect it to open up a bright future for us. So we started to apply it in one of our clusters. As you can see, we used version 3.2, not 4.0. Why? I know the latest version comes with fixes for many problems, but also they tend to have new unknown bugs, which can be critical. If it was only a matter of updating a library, using the latest won't be a problem. But for database or storage system, using the latest can be risky. Also, we cannot upgrade the Redis version on running Redis clusters. So we went for stability, and at the time, it was version 3.2. let's see some of the issues we had with Redis 3.2. There are times when we need to replace the running master machine, the machine containing master nodes. For example, if there is an ECC warning for memory or disk failure on the machine, we have to replace the server even if the Redis server process is up and running. If in the process of replacement, we want to avoid impacts on our services like slow responses or request failures while we are replacing a server machine. We have several ways to replace a server. The easiest way is killing the master process, which will make a slave node a new master. But clients will experience failure to their calls for 20 seconds to even a minute. We don't want to have many clients experiencing failure. Another way is using the cluster failover command, which switches master and slave. As you can see here, the master becomes a slave, and the slave becomes a master. After replacing the original master's machine, host A replicates host B. In the midst of all this switching and replicating, some Redis clients may not be aware that the master has changed. While host A loads an RDB file for replication, its CPU usage hit 100%, so some requests to the old master will be refused. We'll see many clients failing for a few minutes in this period. There is a workaround for this. If we move slots to other master servers and trigger the cluster failover command, then it will be safe. After running the command, we can move slots back to the new master. However, the biggest drawback is that it takes too long time, and it can take a few hours. Also, moving slots makes many rehashing in the master nodes, and it causes slow queries. The second issue we had was the amount of the used memory in Redis cluster, which I believe many of you probably have heard of. Redis cluster uses a salted set for mapping keys with slot numbers. But when there are many keys, the salted set is going to be huge. It can take up quite a lot of memory out of the memory allocated for Redis. The numbers you can see here is in the table are real data. The maximum memory allowed per Redis process is 16 gigabytes. In one of the processes, the used memory was 5.91 gigabytes in our in-house Redis cluster, whereas it was 11.69 gigabytes after we migrated data to Redis cluster. Memory usage doubled. It sounds like we needed to double our memories, double the number of shards and machines as well. I'll be frank with you, I really don't want to have 10,000 more shards if I had 10,000 shards. A good news is that Redis 4.0 uses Redis 3 for the mapping and uses less memory than Redis 3.2. Still, it uses more than the in-house Redis cluster. The third issue we had was the number of maximum nodes allowed. The official Redis document states high performance and linear scalability up to 1,000 nodes. 1,000 nodes. If there are many nodes, the cache traffic can take a lot of network bandwidth. It can be larger than Redis request traffic. However, we have some clusters that have up to 3,000 nodes, including slave nodes. So, what do you do if you have more than 1,000 nodes? There are two solutions to overcome this limitation. One is separating some data out by data type into another cluster. The other one is using client-side cluster sharding, which I'd very much like to avoid, but I want to go over the drawbacks of client sharding again here. So we've shared our experience with client sharding and with Redis cluster. There are 3 ways to implement Redis clustering. There is no silver bullet. It depends on the application logic and the characteristics of a system. Many use a proxy system. Latency can be longer, and it requires more servers for proxy system, but you can make a light and simple client. Client sharding. You can have a short latency and it's cost efficient. You don't need to bring in more servers, but resizing is very difficult and maintaining all the clients requires time and effort. The last option is using Redis Cluster provided by Redis open source. This option uses more memory and more servers, and the size of nodes is limited, but dynamic resizing is easy with this. Again, how to implement Redis clusters depends on your target system. Lastly, I want to cover a bit about asynchronous Redis client. In line, some developers wanted an asynchronous Redis client with the in-house Redis clusters for their async application servers using Armeria. Also, we wanted to provide the in-house Redis client that supports asynchronous I/O. But Redis, or Redis client for Java, doesn't support it. So experimentally, I wrote the netty code in Redis, which I contributed to netty. But many members didn't want to reinvent a wheel. So instead of writing own Redis client, we adapted Letters, an asynchronous Redis client written in Java and built with netty, into the in-house Redis client. We added many asynchronous implementations of internal features on the client. During these tasks, we contributed some code for features and bug fixes to the Letters repo. After we got the in-house Redis client updated, we started applying it in small Redis clusters. While we adapted it, we made an issue, a latency issue. Redis server processes are really fast thanks to its in-memory structure. So in terms of latency, clients play a bigger role. To see how clients affect latency, I measured the latency for Redis and Letters on a Linux machine, and it was 16 microseconds and 31 microseconds respectively. Letters took almost twice longer. I tested the netty code in Redis too, and it showed similar metrics to Letters. Why is the latency in Letters longer than in Redis? Because they use different system calls and different thread models. For example, Redis uses send to, pull, receive from functions in the same thread, whereas Letters makes calls like write, equal wait, read, and fill text, and uses different threads for calling and I/O. Also, it uses bytebuf, netty's buffer management, and JNI too. All of these increase the latency for Letters, making it slower than Redis. This problem can be found not only in a local test, but in production system too, in a similar way. I tried placing a Letters-based client in a small part of the production system and made comparison. Indeed, there are many other influential factors by JVM, like count of thread or garbage collection, but it comes down to the same conclusion. The average latency of Letters is longer than Redis. Fortunately, the difference is not big as 2 folds in this graph, but sometimes the latency can be twice as much. Not only are we seeing high latency here, but more latency peaks in Letters data, from which we can conclude that Letters is more unstable than Redis. Well, then you might wonder, is there any good in Letters? Absolutely. Absolutely yes. Redis has a good throughput. That's why many people write full asynchronous system. Since async applications don't need to wait for a response after sending a request, they are free to send more requests to Redis servers, making the throughput of asynchronous systems higher than that of synchronous systems. Our messaging application can write or read hundreds of keys from Redis with a single API request. This is why we wanted our system to be asynchronous. If an application accesses Redis only once for an API call, then using a synchronous client would be better. Synchronous clients have a short latency, but they block threads. Asynchronous clients have a high throughput but longer latency. And their max response time is not stable by many factors. Nonetheless, we are working on bringing more asynchronous Redis clients little by little. So finally, we've come to an end. Before I leave off, I'd like to briefly share our current status and future plans. We want to bring in more the official Redis clusters into our system. We are working on our Redis cluster manager system to integrate managing modules for both in-house clusters and the official clusters. We are working on bringing more of asynchronous Redis clients and other asynchronous systems like RxJava and RMLia. And of course, we want to test and use Redis 4.0 for some features like Redis 3 and psync version 2 and onlink command. And lastly, there are many other tasks awaiting us, including Redis-related and messaging-related tasks. We are actively hiring software engineers, storage engineers, and for many other positions all around the world. Please check them if you are interested. Thank you. Any questions?
Thank you. That was a really great talk. I had a couple questions. The first is about the anticipator.
Yeah.
So does your anticipator act on client local information or global information?
It's local information.
Okay.
Yeah.
And have you thought about doing global? Have you had any disadvantages to doing it locally?
For global information, we need to sync those information between thousands of servers, but it takes time. So we use it in local information. Each application counting them and checking them by themselves.
Got it. And then the second question I had was just around the change velocity of the libraries and tools that you're using, and how much time you spend maintaining the code versus doing operations.
Code and operations. It depends on the days, and I think about operations we spend maybe 30 or 40 times. We spend some time for operations, and when we don't operate something, we usually write codes. Yeah, and my team is a Redis team, so our responsibility is maintaining Redis-related infrastructure and those kind of systems. Yeah.
And my last question would just be, how big is the Redis team at Line?
There are 7 people in Line Redis team. 4 people are working in Japan, and 3 people are working in Korea. Yeah.
Thank you.
Yeah. With space.
So I have a question about your double read earlier about reading Redis and the HBase. So if the Redis, the timeout you normally expect to return is like in some kind of microsecond, why there's a reason to send the dual write at the same time? Why not wait until the timeout or the failure?
Sometimes if there is a hotkey or if the machine have an issue like ECC memory warning or network problem, then Redis doesn't respond about any requests. So in the cases we use responses from HBases.
Yes, I understand, but
yes.
because it's very rare, so you
Yes.
should be able to avoid 99.9%
Yes.
of your extra read.
Yeah, right.
You really just throw it away.
It's very rare. It's under 1%, and but there are many requests to run server, so 1% is not small requests. Yeah.
Thank you.
Thank you. Yes.
Why Redis cluster takes up so much memory?
Could you use the mic?
Redis cluster takes up so much memory.
Why Redis clusters? Do you mean open source Redis clusters? Why in use? In Redis, in the official Redis cluster, there is a sorted set for mapping keys and slot numbers in Redis source code, and it uses a lot of memory in Redis server process. Yeah. Yes. Yes.
Yeah, so I had a question about one of the slides, the pros and cons slide. You had 3 different scenarios for caching, and I was curious about some of the different use cases that would apply for each of those scenarios that you guys have taken in consideration. So there was a proxy use or scenario.
Okay.
Right.
Proxy.
Yeah, that one.
This one?
Yeah.
Yes.
So are there specific use cases where you're actually caching specific types of cache, whether it's user session data or any other types of objects that you're looking at caching in the stack, where you would use a proxy versus client sharding versus an official Redis cluster? Or in this case, are you only using the Redis cluster for all caching use cases?
Actually, they are not only for cache, but and we store some serialized object into Redis clusters, and for them we use client sharding method, and for storing mutable data we use a client sharding method. And about using the official Redis cluster, it's a kind of experiment of ours. Yeah. So, what was the question exactly?
I'm sorry?
What was the exact question?
No, you actually answered it. I was just curious about different use cases where you're
yes.
taking
Yes.
specific use cases across the stack and
We didn't try proxy system because for using proxy system we need maybe thousands of machines we need. So we didn't try proxy system before. Yeah. Any other questions?
What do you use for real-time notifications or like push notifications?
Some clients connect to the connection server when they are using the right application, or in Android application they are connecting the connection server, connection management server, and if they are connected, we send a notification using the connection, or if they are not connected, we send pushes like GCM or APNS or other push systems.
Do you use Redis PubSub or something else for that?
No, we don't use Redis for push systems. Actually, there are another push system and a team, and this is only about the messaging systems. Yeah.
Did you try using Redis Sentinel before you built your own in-house solution for master failover?
Sorry.
Did you try using Redis Sentinel before building an in-house
No,
solution?
we didn't try Redis Sentinel because to use Redis Sentinel, it needs more servers only for Sentinel. Yeah, so we didn't try it.
Could you give some details regarding Kafka and Redis?
Okay. Here.
Yeah, exactly.
Yeah. When when writing data to Redis or writing data to HBase are failed, we store the writing request into Kafka, and the asynchronous task processor will retry the writing request to Redis or HBase later. Yeah.
Do you think performance-wise Redis would be better?
Actually, we use local Redis queue in the same machine on the messaging server for the queue, but we are adapting Kafka for queuing systems because of persistent. So storing something to Kafka takes more than 1 millisecond. Yeah. Of course, storing something to local Redis queue is more shorter, but local Redis queue doesn't have a persistence, so we are trying to adapt in Kafka for the queuing now. Yeah.
Thank you.
Thank you.
Just in this case, there is some really consistency issue. For example, the applications try to write to Redis field, and the message will go to Kafka, for example, and how long time the key will be write down back into the HBase, because the next request may be read from the Redis field, and the application will retrieve that information from the HBase. But if that is still in Kafka, so that's consistency issue. How do you fix that?
Yes, it's possible. It's possible, but if for adding new items, we write data to both Redis and HBase. But for updating mutable data, we don't update data to Redis. Instead, we delete the data from Redis and we update the data for HBase. So it decreases the inconsistency. And as you said, it's possible there is an inconsistency for a short time. So storing something by background is very scary thing. Yeah, but it's sure, but it's very helpful to decreasing response time. And in messaging system, response time is the most important factor than other features. So if you want more durability, dual write may not be a good solution. Yeah.
Thanks.
I have another question for you.
Yes.
So I like the way you build your real-time monitoring system that
Yes.
you can go to resolution of in a second. I have a question about how you detect the hack key or the hack command bursting pattern. Because normally this will happen in like only a few milliseconds and it's gone. How can you detect it and be able to log it?
The hack key and it's basically it's second precision, and if there are more operations, I mean Redis requests or more connections than previous few seconds, then it recognizes it or hack key situation. And usually the hack key opens like this. It's not only the difference is not small. Usually in there is a hack key, then difference is very large. So we can find them by the second precision detecting.
So the detection is based on the data returned back from the info command?
Yeah, right.
Thank you.
Okay, thank you.